Here, I am making the video explaining question number 3 from the take-home exam. The question was to find general expressions. Part A was to find general expression for the expectation value of x for the simple harmonic oscillator. So, for the simple harmonic oscillator, we have found an amazing thing, which is the raising and lowering operators. So you can express the function of x in terms of the raising and lowering operators by this expression here. The x operator is equal to square root of h bar over 2mw times a plus a minus. So what we'll do then is we will operate on it and say, we'll operate on the wave function squared and say expectation value of x equals the integral from negative infinity to infinity of psi star times h bar over 2 w square root times a plus a minus times psi dx. Okay, so now we can pull out the constant, but this equals square root h bar over 2mw times psi a plus psi a minus psi dx. And as you can see, what this will do is it will make this one an n plus 1, and it'll bring out the constants. And it'll make this one an n minus 1, and due to the orthogonality principle, this integral is going to come out to 0 because they're not, m doesn't equal n in this case. So that's part A. Move on to part B now. Part B is to find the expectation value of x squared. I should have left that there, but so we'll square the operator, call it h bar over 2mw times a plus a minus squared. This equals h bar over 2mw times a plus squared plus a minus squared plus a plus a minus plus a minus a plus. So now we operate again. So we do expectation value of x squared equals the integral from negative infinity to infinity. Pull out the h bar of 2mw times psi a plus squared plus, psi, this is a psi star, plus psi a minus squared psi plus psi a plus a minus psi plus psi a minus a plus psi dx. Alright, these two orthogonal going to go to 0, and then what happens here is that I forget the constants that come out, but what's going to happen is that it's going to be equal to h bar over 2mw times the integral from negative infinity to infinity of
Ready.
Okay, now we're back. My camera ran out of storage, so I'm just going to continue from where I left off. So, what we're doing now is these pretty much keep it at the same energy level, but they pull out a constant, so it's going to be n psi. And just remember that all these are psi stars. I just don't feel like writing a star because it's a real function anyway, especially in this case. And then I will pull out an n plus 1 for this one brings an n, this one brings an n plus 1. Oh, yeah. So now we're back. My phone keeps running out of service, memory. So these each go to 1, and so now we have h bar over 2mw times n plus 1. So it's going to be h bar over 2 mw times 2n plus 1. And that is the answer for B. Now we are going to find the expectation value for the Hamiltonian. And again, we do the same thing with the operators, and we write the Hamiltonian in terms of the operators, which I need to find out right quick. Sorry about that. So the Hamiltonian in terms of the operators is equal to h bar w times a plus a minus plus 1/2. So we're looking at that's just the Hamiltonian operator actually. But what we're looking at is the expectation value equals the integral from negative infinity to infinity psi star times h bar w a plus a minus plus 1/2 psi dx. Now, we got the, we can distribute through, so we got psi times h bar w times a plus a minus psi plus 1/2 psi, all times psi again. So we got this is going to be h bar w on the outside times the integral psi a plus a minus psi plus 1/2 psi squared dx. So this again, we pull out the constant. Alright, sorry my video actually is in 3 videos, but now it's now I can wow, everything actually looks backwards on this because now I'm using a webcam because my phone completely ran out of space. But I will explain it to you backwards. It's just the end here where I've pulled out the n constant from operating plus and minus on here and distributed, and both of these integrals go to 1, so now we're just left with the constants, and you obtain the expectation value of the Hamiltonian to be h bar w times n plus 1/2, which is actually En, so we've derived En for the simple harmonic oscillator. Thank you. See you tomorrow.